Hello students, welcome to this video where we will discuss Chapter 6, Transportation and Assignment Problems. We're going to leave transshipment problems out. So within this chapter we're going to look at the transportation model, we'll look at computer solution for transportation problem, and then we'll go look into the assignment model with a computer solution for that model as well. We will be using Excel and Solver specifically to help us work out possible solutions. First thing we're going to do is the transportation model. So in this this type of transportation problem, there is products that's transported from a number of sources to a number of destinations, and we want to minimize the possible cost. So it is in essence a linear programming problem where we try to minimize the transportation cost. Each source is able to supply a fixed number of units, and each destination has a fixed demand. This model has constraints for supply at each source and demand at each destination, and then we're going to introduce the costs of sending product from each destination or each supply to each destination. So here's the example that we'll work on. It's the wheat shipping example. We have 3 grain elevators with supply. So Kansas City has a supply of 150 tons of wheat, Omaha 175, Des Moines 275. A total of 600 tons is available, and we have 3 mills that demand a certain amount of wheat product from the supplying grain elevators. So Chicago 200 tons, St. Louis 100 tons, and Cincinnati 300 tons. Supply equals demand. So typically that's a balanced type of a problem. There are situations where it would be unbalanced, and we'll look at that as well. And we have within our transportation problem, we have various costs. We can look at it cost $4 per ton to ship from Des Moines to Chicago, so that's the smallest cost. So definitely we want to, most likely we're going to see some items shipped from Des Moines to Chicago. And then perhaps a higher cost like this, Des Moines to Cincinnati, much higher cost. We probably won't see any product shipped from there. So the illustration of this situation or this problem, basically here we have the 3 grain elevators. We have various mills that require the wheat product, and you can see that of course if the mills are closer to the grain elevators, the cost is going to be reduced, or it's going to be a little cheaper. So we develop a linear programming model that is going to be set up using Excel like this, where we try to here are the grain elevators. Kansas City has 150 tons, Omaha 175, Des Moines 275. Oops. And over here we have this Cincinnati, Chicago needs 200, St. Louis needs 100, Cincinnati needs 300. And we're going to determine how much of the wheat products are going to be shipped from each grain elevator to each mill at these costs here. So we're going to introduce some functions which are explained in the PowerPoint. There's an illustration of how that's set up, but we'll look at this one here. So our demand, grain shipped, is going to be basically the sum of these 3. It has to equal 200. This grain shipment, we can look at that formula, D5, D6, D7 is basically the sum of these 3 cells. Same thing for Cincinnati. The grain shipped is adding these ones across. But this total cost is going to be, there's a nice Excel function, it's a sum product. So it's going to multiply corresponding cells with each other and then add them up. So basically if we ship, say 100 items here, we know that the cost is going to be $6 per ton, and that's would be a total of 600. So instead of having a function that's going to look at multiplying this cell with this cost and this cell with this cost, this sum product does this all for us. It is sum product that's basically C5 to E7 multiplied, or colon, comma, multiplied by K5 to M7. So we need to make sure that our matrices, our cells, are set up this way. So let's take out this 100. And let's introduce our solver in this, where it's a minimization problem. We're trying to minimize our total cost by changing values in here. Our constraints are going to be that our grain we shipped is going to be equal to the grain that is being demanded, and the grain that we have in supply is going to be equal to the total supply we have from those three destinations. So we click OK. This is our two constraints. And then we just need to solve this. There it is. Minimum cost to do this is $45.25. You can see that we did ship most of our product from Des Moines to Chicago that Chicago needed. And it gives us values for each. So the solution is Des Moines to Chicago, 175 tons. Kansas City to Chicago, 25 tons. It gives Chicago the 25 tons. We can look at the total amount that Des Moines had, 275, which was how much they had supplied. So this is a balanced situation that we could that we're going to use to determine the minimum cost of shipping those products. So questions could ask, well, how many where does Kansas City send their products? Where does Omaha send their products? And where does Cincinnati get their products from? Kind of thing. And it's basically looking at these numbers here. Now, an unbalanced situation occurs when perhaps demand is different than supply, or supply is different than demand. So what we're going to do is we can change these numbers in yellow. Say, for example, Cincinnati needs 350 tons. We can see that this is an unbalanced situation right now. We set this up in Solver the same way. We're going to get an error message. Solver could not find a feasible solution. It does, however, but supply or demand constraint is not fully met. But this tells us that Cincinnati needed 350, but they only get 300. And there's changes here in the other variables as well. So some of the assignment questions could be based on not having a balanced situation. So let's change this back to 300, making sure that equals 600. Yep. Or perhaps this is a more likely situation, is that now there is a change in the cost. We really like having, well, let's change this back and solve. Yeah, there's our original solution. We shipped 175 tons from Des Moines to Chicago. Now let's imagine that that transportation network is no longer possible. Maybe there's road construction, maybe there's cost or a strike involved. For whatever reason, it's prohibited that we can ship from Des Moines to Chicago. So we can add a constraint to make that possible. Or the best way is to make this just a really, really, really large number. So large, in fact, that we're basically telling the system, don't ship from Des Moines to Chicago. Originally, we shipped 175 units, so now, or 175 tons, now that has to come elsewhere. So when a cost or a transportation route is prohibited, we enter a really large number. I'm just entering 6, 7 nines in there. So we solve this. Basically, it changes everything. Our cost has gone up because we took out a really inexpensive route. Chicago is getting their demand met. St. Louis, Cincinnati, same thing. Kansas City, Omaha, Des Moines are shipping what they have in supply. So everything is balanced. Our costs have gone up. So if we change this cost back to 4, where it was originally, we can run this again, and there's the original cost. Now, if, for example, Omaha to Chicago, that route was no longer allowed, it's not going to change anything because we're not shipping there. So even if we increase the cost here, it's not going to have any bearing on the final solution. It's still 45.25. So let's change that back. It's 7. So those are the possible questions that are the extent of which we need to understand transshipping problems, is to set up our Excel file and to run solver with the various constraints. The objective function is listed there, and the various costs.